thank you for the introduction, Peter. So, as mentioned, I will speak about how maybe we can accelerate deep learning inference with Posit numbers. So, I'm a PhD candidate at Barcelona Supercomputing Center. So, for the outline, firstly, I know that some of you know Posit numbers, but I will have to hopefully quickly introduce them. Then I will expose current problems and motivation, and we will dive into implementations, the early results that we obtain, and then we will conclude. So Posit numbers, like floating points, the one you know, the IEEE, intend to represent real numbers. So the claim from the authors is to be a drop-in replacement. The idea is to have to better sync the repartition of the bit inside the number, but being more data-driven and problem-driven than just a very general purpose arithmetic representation. So, and on top of that, in the standard, there is a very large accumulator unit that is called the quire that allows you to perform fuse dot product. And it tries also to avoid the design flaws that are with the floating point number, like 8 million not numbers in case of the single precision. So how does a Posit look like? So unlike the floating point, the IEEE floating point, you don't have a Posit single, half, and double precision. You have many configurations of them. You can choose a bit width and the exponent size inside of it. So it's denoted here, Posit and ES. So this allows you to find the best Posit representation you can have for a problem. And this is called the tapered precision. The difference with floating points, IEEE floating point, is that the scale, the exponent, is not coded as a signed integer. It's a Golomb-Rice encoding that allows you to, I will explain after what it allows, but this implies in the hardware to have variable length internal fields. So you have a sign bit, then you have the regime that can push the other part, and so if you have still place, you can find an exponent and a fraction part. So at the end, you can still represent a floating point number, it's a mantissa and a scale. In a hardware point of view, what does that mean? If we suppose that because there is more entropy per bit in a Posit representation, a 32-bit Posit number could beat a 64-bit floating point in a scientific application. It could, it's not always true. So this directly means reducing the amount of caches, the throughput, the power consumption, and it can mean that it reduces the hardware resource of compute units. Not always true. So, quick reminder, I want to show here that the communication dominates arithmetic in all the microarchitectures, or many of them. So in the left array, we can see that the memory operations are order of magnitude slower in terms of latency than the arithmetic operation. And the same for power consumption. This implies 63% of the energy spent on the system due to communication. But we don't stop in that problem, so how can we solve them? Reducing communication. There are many ways that are being studied at this moment. You can either shift very hardly the paradigm into the in and near memory computation. You can do quantization, transprecision. But in our study, we will study the impact on just changing a drop-in arithmetic and study the impact on the overall system, like power consumption. And we will focus on AI because, I mean, the AI is a surge interest is ever growing, and also because Posit are, I think, a good candidate for the neural network case. I will explain in the next slide why. So the first reason Posit is good for AI. So they have this so-called golden zone. So firstly, the IEEE floating point, as you can see in the green line, they have a very constant and very large accuracy over 8 decades for the single precision one. unlike the Posit, that due to the Golomb-Rice encoding, you can, by this encoding, you can gain place in the exponent part, because you know that your value will be near 0, for instance, for a value. So if you reduce bit in the near this value, you have more place for the Mantissa part. So this creates these shapes of distribution of Posit, and also the accuracy of the Posit that is entered and a value. And this Gaussian distribution match the neural network weight distribution. So this as a result of augmenting the entropy per bit, and that leads for more information per word. I mean, if it was suited to an application, less communication, less storage. Maybe you can stay on chip all the weight of a neural network. And metrics to compute this in a problem are, for instance, the Shannon max entropy. The second reason why Posit are good for AI is they have a nice hardware approximation of sigmoid, that is fast sigmoid. So as you see, the sigmoid is quite complicated division and exponential and some computation. In case of Posit, you can just negate the sign bit, do a logical right shift by 2, shift right to 2, and that's all. It's about 1 clock and some gates in our lookup tables. It looks like this, the blue shape compared to the red shape. The third reason, so might be obvious, but in neural network, in the gray part on the white plot, we see that FMA is biggest part in this plot. FMA in neural network stands for multiply accumulation. So this means that every neuron is actually performing a multiply accumulation plus activation function. So in a classical way, like for instance in GPU, there is a large accumulation performed with FMA. So you still accumulate an error around accumulation. So because you do rounding after every accumulation. The idea here with Posit, in the standard Posit, is to use the quire, the exact multiply accumulator unit that I call, to postpone the rounding and to have only one rounding at the end of the accumulation. It looks like the bottom plot. You have a big scratch pad. You accumulate small values inside, and you shift them by the scales, and you put them inside the scratch pad. Right now, the most interesting part, the implementation. So this is our setup, hardware setup. So we have two Alpha Data 9v3 FPGA boards that are in the most beautiful supercomputer of the world, the Industry 4. Here I will explain how I use CAPI and Snap to accelerate the acceleration. So we will go into this nice stack of technologies. The first one is CAPI. So CAPI, as mentioned before, allows to do the accelerator be part of the host system by putting the driver into the hardware, and it does all the job as translating the virtual address, and we just have address. We don't care. I mean, we know that it will go on the process virtual memory space. But still, CAPI will not allow me to program fast. So I decided to use Snap. That I see it as an axis bridge. So axis bridge, this I know as a hardware developer. On top of that, Snap allows to add an abstraction level. So when OpenCAPI will be released on Snap, I don't need to change my code; it's already in place. Then I add some helpers because axis full, as you know, axis memory map is complicated. So I add an axis string bridge, and then I can the cloud part here. I can just plug and play, and I can develop in weeks an acceleration solution to evaluate the overall system. How do I verify my modules? So the classical one test bench per module. You might know this pattern. So so we have the source and sink that in this Yeah, these vectors, these oracles, are generated by software languages that incorpores the Posit inside. I mean, there have been Posit libraries into Julia and Python. They generate this, and at the end we have a bit-to-bit co-verification. And thanks to the Power Service Layer Simulation Engine, we can replace this source and sink by the actual software code that will be run into the host system. That allows to gain a lot of time. So this, you know, as the most famous and easiest neural network topology, a fully connected multi-layer perceptron. But this can be seen like this in FPGA. So the idea is just to map the topology of the neural network directly in the FPGA with a synchronous data flow graph. It works if it fits, otherwise it's more complicated, because we know that a neuron, like I said, is equivalent to an exact multiply accumulate unit. The links I made by the access stream protocol, which is access stream compliant, and these we can generate every neuron per layer, every number of layers, every posit width, every activation function, and every rounding scheme in all of these EMAC. So I present how it does an EMAC. EMAC is neuron. So as the formula mentioned, it's just a product of activation and weight that is passed into the activation function. So we see directly in hardware how it's mapped. There is weight, ROM, activation, they decode, you multiply them, you go into the exact accumulator that is called the quire, so you do zero rounding in every step, so you can have very small posit. You do only one rounding at the end of the quire, and then you go into the sigmoid. Here is another version for experimentation purpose that has a rounding, no FMA and no exact accumulation. It's just to see how it performs without this, to do comparison with floating points, for instance. And I also want to show you that I did a zoom in this black arrow, that's just to say that we use parametric system Verilog interfaces. So everything is plug and play. You can connect the plus to multiply, and just by one line of code, it's an interface. And it will create all these necessary signals that are maybe not sufficient. I will focus a little bit on the product part, just to see how it could look like. So, like a floating point version, you take operands and have results, and everything is parametric. So for results, these two arrays show that with two versions of the neuron, the one 4 bits with exact accumulator and one with 8 bits without the accumulator, we maintain the 90% accuracy of the MNIST classification problem. So these frameworks allow to evaluate all possibility of neurons and to see if it still maintains accuracy. So here we can already answer part of the problem I mentioned before. So we see here that we have half bits per neuron. So this means half bits communication in PCI Express and half size of DDR allocation. But 4 bits neural network is only consume 4 bits. It only consumes 4 bits. So we want also to saturate the PCIe link, like I saw in the previous presentation. So to do so, we don't want to change all the design of neural network MLP. So we apply data parallelism. And because also we want to use all the power of my CAPI snap of a lot of gigabytes per second. So here a lot of numbers. What does that mean? I just want you to focus on the first line, I mean the highlighted lines, but they are not well highlighted, but some of them are bold, like the Posit 4-bit and the IEEE 16-bit. We can see that both of them maintain at the end an 80% accuracy of the MNIST classification problem. But the 16-bit version of IEEE for sure implies 4 times the allocation time, a needed throughput of 6.2 gigabytes per second, so it occupies more bandwidth in case of multi-hardware and FPGA. If you can use less bandwidth, it's better to let bandwidth to other actions, and all of this for the same number of images per second. In red, the number are the one that I extrapolate. I don't have them still work in progress. And this is if we take the problem in the other way. If we can saturate the link by putting enough multi-layer perceptron, still if we look at the same line, same accuracy, still we have 4 times more allocation size. This is the number of neural networks needed. And we have, for sure, 4 times more image per second, so it's faster. How does it look like? One B stream, just to show you. So 16 neural network of n-bit and exact accumulator. In yellow is CAPI, pink is SNAP, and then I put color on 3 neural networks, red, green, and purple. Still, this is the smallest ultra scalars. And to conclude, so thanks to CAPI and SNAP, we can really fastly, quickly, but RTL logic and evaluate it in weeks in a very powerful system. So we built a framework to build every fully connected multi-layer perceptron AI neural network. So the problem is right now we only evaluate Posit. Early results look promising, but the comparison with floating points is hard to do. If we want to put in hardware, it's hard to find a library that allows a totally IEEE compliant. There are a lot of hacks behind this. And my numbers of accuracy, I get them from a library that I don't trust a lot. So maybe if I use a more robust one like Subfloat or Berkeley, maybe I will find that with 5-bit it performs 90%. So that's why it's in red before. But let's suppose it works. So we show that we maintain the same accuracy with 4 times less bits. So we have 4 times less storage, power consumption, and communication time. And this is what we wanted to show, that if we change an arithmetic, a drop-in claim drop-in replacement arithmetic, we show that communication dominates less arithmetic. So it's not shifting paradigm also is also about exploring arithmetics and evaluating the full system. But still, I don't really know how to measure the power consumption of the system. So if someone wanna help me on this, I'll be happy. And thank you for listening. I hope you have questions.